welcome to CEC lectures. Myself Dr. Priti Jagwani from Department of Computer Science, Arbet College, University of Delhi. So, in my previous lecture we looked into some categories of multiple access protocols and the requirement of these multiple access protocols. So, now we will be kind of dwelling inside these different categories. So, let us have a quick recap that the objectives of those multiple access protocols which we are going to cover are optimization of transmission time, then minimization of collision and avoidance of crosstalks. And within these multiple access protocols we have three categories. So, one is random access protocols consisting of ALOHA, SASMA, SASMA CD and SASMA CA. Then we have controlled access protocols which includes reservation, polling and token passing, and the third category is about channelization protocols including FDMA, TDMA and CDMA. So, let us look into these categories now. So, when I am talking about random access protocols, so random access protocols assign uniform priority to all the connected nodes. So, it is having all the nodes or all the stations are having kind of priority on a in a uniform basis, and any node can send the data if the transmission channel is idle. No fixed time, or we can say no fixed sequence is given for data transmission. That means this uniform priority is going to be kind of given to all the connected nodes, and these nodes can send the data if the transmission channel is idle. Now, what are these what these random access protocol consist of? There are four random access protocols. One is ALOHA with two of its versions. One is slotted ALOHA, another one is pure ALOHA. We will be looking into it soon. Then we have carrier sense multiple access SASMA. Then we have carrier sense multiple access with collision detection SASMA CD. Then we have carrier sense multiple access with collision avoidance, which is SASMA with CA. So, ALOHA, slotted ALOHA, pure ALOHA, carrier sense multiple access CSMA, SASMA, carrier sense multiple access with collision detection SASMA CD, CSMA CD, and carrier sense multiple access with collision avoidance, which is CSMA CA. These are the four random access protocols. The next category was controlled access protocols. So, controlled access protocols allow only one node to send the data at a given time. Before initiating the transmission, a node seeks the information from other nodes to determine which all are the stations they have kind of which stations has the right to send, or they have kind of wish to send, and this is done, this exercise is done in order to avoid collision of messages on the shared channel. So, before initiating transmission we can say an information looking for who all wants to transmit is being kind of seeked. So, this is controlled access protocol, and this allows only one node to send the data at a given time, and which station will be assigned the turn, or which station will be assigned the right to send is going to be determined by three methods, which are the three techniques under controlled access protocols is reservation, then we have polling, and the third one we have is token passing. So, who is going to transmit the next is going to be decided by either by reservation or by polling or by token passing. Third category was channelization. So, channelization basically a set of methods by which the available bandwidth is divided among the different nodes for simultaneous data transfer. Now, this kind of division can be of time, or it can be of your frequency, and the three time division the three channelization methods are FDMA, which is frequency division multiple access. Next one is time division multiple access, more commonly known as TDMA, and the third one is code division multiple access, which is CDMA, out of which frequency division, multiplexing in a different form, and what do you mean by time division multiplexing, that we have already covered in our previous lectures. So, these multiple access protocols are having random access protocols, controlled access protocols and channelization protocols. So, moving further, let us begin with random access protocols. So, as I have told you that these random access protocols are going to assign uniform priority to all the stations or to all the nodes which are connected. That means any node can send the data if the transmission channel is idle, and no fixed time or no fixed sequence, no fixed slot is given for the data transmission. So, in this approach we can say all the stations have equal priority, and transmission decisions are based on the state of the channel. That means whether your channel is busy or your channel is idle. So, basically we can say these random access protocols, they do not have any fixed order of transmission, no fixed time slot assignment. Now, why I am insisting on the word no fixed time slot assignment? Because we have a slotted ALOHA also in which slots are there, but these slots are not assigned to any of the kind of stations, we can say. So, 4 random access protocols are ALOHA, SASMA, SASMA CD, SASMA CA. So, first of all we will be looking into ALOHA. So, ALOHA, it is a protocol which is, we can say, designed for wireless local area networks, which is wireless LANs and the shared media. And in this is, I can say, it is the simplest form of the MAC layer protocols, also having many of its consequences, we can say. So, in this, multiple stations can transmit simultaneously, which is going to kind of lead to heavy kind of amount of collision, we can say. So, basically your ALOHA is what? Your ALOHA is a packet switching system, and the time interval which is required to transmit one packet, here we are calling that time interval as a slot. And this ALOHA is a random access technique because multiple stations can transmit simultaneously. It is not like that this is this particular station A is having priority to transmit, and the station B is going to wait. No, it is not like that. So, it is actually a random access technique. Now, looking into what are the different versions of this ALOHA protocol. So, there are 2 versions of ALOHA, which are pure ALOHA and slotted ALOHA. So, with these 2 versions, let us try to understand these both the versions, and we will be looking into the difference of these. So, in pure ALOHA, if we look into the key mechanism in a step by step manner. So, first of all, let us see what do we mean by pure ALOHA. So, the mode of random access in which any user can transmit at any time is your pure ALOHA. So, in pure ALOHA, the nodes transmit frames whenever there is a data to send. Now, what happens in this situation? When 2 or more nodes transmit the data simultaneously, and the channel, of course, we have what we are considering is a shared channel. Now, then there is a chance of collision. Why I am saying there is a chance of collision? Because they may or may not collide, and the frames can get destroyed. And also in pure ALOHA, the sender is expecting an acknowledgement from the receiver. If acknowledgement is not received within a specified time, the sender node assumes that the frame has been destroyed, and this kind of mechanism we have also seen in our previous data link layer protocols when we were studying them, which are kind of utopia, the simplest protocols and so on and so forth. Also, if the frame is destroyed by the collision, or as we are considering only the situation of collision, and this is related to our assumptions which we looked into in our previous lecture. So, if the frame is destroyed by collision, the node is going to wait for a random amount of time, and then it will send it again, because it has not kind of we can say received its corresponding acknowledgement. Now, what is going to be the waiting time? So, waiting time may be random, otherwise the same frames will collide multiple times. So, it is kind of a random amount of time for which your sender is going to wait, and then it will retransmit if it is not kind of we can say not received the acknowledgement. So, in pure ALOHA, when the timeout period passes, each station must wait for a random amount of time before resending its frame. Thus, this randomness is going to help the protocol pure ALOHA to avoid more collisions. Now, in these kinds of situation, when there is a collision, we need to look into one important term which is known as vulnerable period. So, vulnerable period is so what is that period? It is the maximum interval over which two packets can overlap and destroy each other. So, this is what the vulnerable period is. I repeat this definition. So, vulnerable period is the maximum interval over which the two periods can overlap, the two packets can overlap and destroy each other. Now, in pure ALOHA, the vulnerable period is 2 slot times. Let us see how. So, a station transmits a frame whenever it has some data to send. Since there is only one shared channel, there is always a risk of collision between frames from different station. Now, in order to understand the vulnerable period, let us try to look this with the help of a figure. Now, here you can see that there are kind of some different stations, or different packets are coming. They can be from the same station, from the different stations. So, the horizontal line is representing the time, and here we actually have kind of 3 packets. One is the packet A, another one is the packet B, and third one is the packet C. Now, let us say your packet A is inside, packet A is transiting, is in transmission at, and it started from T0 time stamp T0 plus T of P, and it is going to kind of get till T0 plus 2 Tp. So, start of packet A transmission happens at T of kind of P, we can T of P we can say, and in which situations this packet A is going to collide with packet B or packet C. So, by kind of considering packet A at one horizontal line and packet B and packet C at another horizontal line, we can say if the the end part of the packet A B is going to it can collide with packets A is packets A is first part, or it could be otherwise with packet C. So, basically our vulnerable period is going to be 2 slots where Tp is 1 slot. So, 1 slot packet A is having a probability of collision with packet B, and in the another slot it is having the probability of collision with packet A, packet B as well as packet C also. So, this is what the vulnerable period, as you can see in the on the screen, is vulnerable period of pure ALOHA, which is equals to we can say 2 time slots. After 2 time slots the vulnerable period is going to be not going to be there. So, the key mechanism of this ALOHA says when a user sends a packet, whenever it is ready, it will start transmitting immediately. The receiver responds with an ACK, which is the acknowledgement if the frame is received correctly, Now, how these collisions are going to happen and how they are going to be handled, if no acknowledgement is received, then in that situation the sender assumes that a collision has occurred, and this is also having one particular mechanism as known as random backoff. So, random backoff says that before retransmitting, the sender waits for a random backoff time to reduce the chances of repeated collision. That means there is no fixed time, because if the time is fixed, then let us say packet A is being collided with packet B, and both the stations have sensed it that there is a kind of a collision which has happened. They both kind of waited for the same amount of time because the waiting time is fixed, and then they both kind of transmitted packet A and B again, and then obviously they are going to collide. So, in this situation we call the mechanism as random backoff, in which before retransmitting the sender waits for an random backoff time in order to reduce the chances of repeated collision. Now, with this, if we want to summarize the features of pure ALOHA protocol, so the first one is the random access, which says devices can send data anytime without waiting for a particular time slot to begin or a particular time slot to get end. Then the coordination, the transmission is completely uncoordinated. No central authority or a coordination mechanism is going to exist in order to control or in order to monitor the transmission. But with its kind of easy to implement policies, this is kind of very suitable for low traffic system, as it is a very simple protocol. Another feature of ALOHA is its persistent retransmission. So, persistent retransmission says the devices retransmission after a random delay if a collision occurs, and even in the next chance also, if there is a collision occur, then the devices will retransmit. So, that means the retransmission is, we can say, persistent. Then it is kind of, it is a protocol which is contention based. Contention based in the sense collision are going to be there, collisions are inherent, and then obviously they are going to be resolved using the acknowledgement and the retransmission mechanism also. So, random access, uncoordinated transmission, simplicity of the protocol, persistent retransmission, and contention based are the features of this pure ALOHA. Now, in order to as we have seen with the help of a figure, we want to look closely into this vulnerable time, because this vulnerable time is going to give us kind of efficiency of this pure ALOHA. So, let us look into this vulnerable time as far as kind of its mathematical expression is concerned. So, vulnerable time is the time of collision, we can say. So, in collisions in pure ALOHA are going to occur, or may occur, if the packets overlap at any point of time. Now, let us say each packet is going to take one time unit, which is denoted by TP, to transmit, and if a user starts sending a packet at time T0, any other packet which is generated in the interval from the starting of the first interval to the ending of the next interval, and that ending of that particular packet, and that interval is T0 to T0 plus Tp. So, any packet which is generated in this interval, which is starting T0 ending T0 plus Tp, is going to get collided with the beginning of the original packet. So, this is a scenario in which we have seen the figure previously, and the packet B was colliding with packet A. Now, any packet generated in the time interval T0 plus Tp and T0 plus 2 Tp will collide with the end of the original packet. Now, please remember the scenario of the situation in which the packet C was being collided with packet A. So now if we want to calculate the vulnerable period for a packet in pure ALOHA, we need to let us look into this figure again. So the packet A, the transmission time is from T0 to T0 plus Tp. So any interval, any packet which is going to be generated within this, so Tp is the transmission time. So any packet which is going to be generated in the interval T0 to T0 plus Tp will get collided with the first half or beginning of the packet A, and which is here the scenario of packet B and packet A. Now moving on the right side, if the packet is being generated in an interval from T0 plus Tp to T0 plus 2 Tp, which is your packet C here, that packet C or that type of packet is going to collide with the kind of later half of the packet A. So looking in this situation, the vulnerable period of this pure ALOHA is the time in which the packets are going to overlap. So vulnerable period for a packet in pure ALOHA is going to be 2 into Tp. If another transmission starts within this vulnerable period of time, which is having an kind of interval of 2 into Tp, both the packets will be destroyed. So that is why I have told you that it is twice of a slot. Vulnerable period for a packet in ALOHA is twice of a slot. Now with this formula or with this expression in hand, that the vulnerable period for a packet in pure ALOHA is 2 into Tp, we need to calculate the throughput of pure ALOHA, and hence we will be kind of able to look into the throughput and hence the efficiency of pure ALOHA. So the efficiency of the pure ALOHA can be calculated using probability, and this probability is kind of, we can say, controlled by the distribution through which your frames are being generated. So throughput, which is commonly denoted by S, is going to be a multiplication or a product of G multiplied by E to the power minus 2G. Now what are these kind of variables here? So S is actually throughput. Here throughput is nothing but the successful transmissions per packet time, and G is average number of packets generated per packet time. So average number of packets are generated, again we are using a probability over here. Maximum throughput is going to be when. So throughput is maximized when your G is equals to 0.5. So taking this Z is equals to 0.5, your maximum throughput, which is S max, will be 0.5 into e to the power 2 into 0.5 minus of 2 into 0.5, which is e to the power minus 1. And if you calculate this whole kind of expression, it is coming up to 0.184. This essentially means that only 18.4% of the channel capacity is effectively used for successful transmission, while the rest whole is wasted due to collisions, because this is the only kind of time in which your packets can be kind of, we can say, saved from the collision. So maximum throughput here is only equals to 18.4%, which is, I am sure, is very less than what we can get using some different techniques or using some other category of the protocol. So in pure ALOHA, the point, or we can say the bone of contention here, is the low throughput. Even at the maximum capacity, it is only 18.4%. Rest of the channel capacity is wasted due to collision. Now with this, as we have looked into this ALOHA protocol into in quite detail, let us try to look into some of its advantages as well as disadvantages. So advantages is it is obviously simple to design and implement, because simplicity is one of the basic characteristics of this. Then it is very suitable for low traffic scenarios, because obviously the capacity or the throughput of the channel is very low. So then low traffic scenarios, ALOHA is, we can say, is suitable. Also it works well in the environments when in which the transmission times are quite unpredictable. Then also your ALOHA, we can say it works well. Looking into the disadvantages, the biggest disadvantage obviously is very low efficiency, which is maximum we have seen is 18.4%. Then obviously there is a high probability of collisions under heavy traffic, and that is why this ALOHA protocol is not suitable for kind of heavy traffic scenarios. That is only suitable for low traffic scenarios. And also if application is a real time application which requires a guaranteed delivery, this protocol is a complete no for all these types of situation in which a guaranteed delivery is required, and all those kind of real time application. So yes, with its very limited kind of applicability nowadays, we can say this protocol is not much into use, but yes, still it provides as a kind of valid and a solid base for understanding other protocols which are slotted ALOHA and others random access protocols we will be covering in our next lecture. So here in this lecture we have looked into the various categories of multiple access protocols, which are channelization protocols. Then we have random access protocols, and then priority based protocols. Within this random access protocol, we looked into one version of ALOHA, which is pure ALOHA. The next version, which is your kind of slotted ALOHA, and other SASMA, SASMA CD and SASMA CA, all these other random access protocols are yet to be covered in our upcoming lectures, and here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next with more protocols. Till then, take care. Goodbye.